Welcome to MEI Mechanics. We're on the topic of forces and moments, and this is video 1.2, moments and couples. Now, so far we've always been assuming or modelling objects as being particles to have no size, and therefore any forces acting on those particles are acting at the same point because it's a point particle. But what we're going to think about now is what if we've got a body which is rigid but is extended in space, so not just a single particle but an object with some size. What will happen then is that the forces could be acting at different points on that shape, and that can have an effect on what happens, especially when we're thinking about whether the object is going to turn or rotate. So here's a little example to consider to start off with. We have two characters here on this seesaw. Clearly the one on the left is larger, has more weight than that poor little fellow on the right there. So when we draw this diagram, then we're going to have several forces acting on this plank. There's going to be this weight over here, maybe call that W1. There'll be a different weight over here, W2. So we're thinking about the place at which the force is acting now being significant. The plank itself may have some weight. We might model it as being massless, but more likely there'll be some weight associated with the plank as well, so maybe just call that W. And then on the thing which it's resting on top of, there'll be a reaction force acting upwards. So if this thing is in equilibrium, then one thing that must be true is that all these forces must add to zero. But there's more going on than that now, because there is some kind of turning effect happening. We are going to consider what's called the moment of a force, which is the turning effect of that force. Now, to calculate the moment of a force, we need to consider not just how large the force is, but also how far away the point of action of that force is from the point at which the rotation is occurring about. Something's called the pivot, or indeed about any point at all. Often we will be thinking about turning moments about a pivot, but in fact we can pick any point at all in space and calculate the moment of a force about that point. But depending on where we choose that point, that will change what the moment of that force is. Okay, so in this situation then, if we take a line which is perpendicular to the direction of the force, then we just need to consider this distance d, which is the distance from the point at which we're considering to the point at which the force is acting, okay, in a perpendicular direction. So in that case we have the moment equal to that force times the distance, okay, and the units are therefore Newton meters. Now obviously the turning moment could be anti-clockwise or clockwise. So in this case we can clearly see that this has got an anti-clockwise direction, and we generally take that as being positive, although I would recommend to be on the safe side, always say anti-clockwise or clockwise, which you can shorten to ACW or just to CW for clockwise. So here's an example then, and we're being asked to find the sum of the moments of these forces about x. Now we'll start over here. We'll start with this 50 Newton force, because this is already directed perpendicular to this line, and so for that force, which is the anti-clockwise force, we simply have 50 times 0.3. However, for this other force, we can't just multiply 10 by 0.7 because this force is not acting in the perpendicular direction. So we've got two choices, and this method one that we're looking at here is to do this. We just imagine extending the line that force is acting along, so that we can then construct a perpendicular here, like that. So we're forming this right angle triangle, and from our basic trigonometry then we can see that this side will have a length equal to 0.7 times sine 60. Now the other thing to note here is that this force is trying to turn everything in a clockwise manner, so we're going to stick a negative sign in front of that as well. So we have 10, the size of the force, multiplied by the perpendicular distance, 0.7 sine 60, and that gives us an overall force of 8.94 Newton meters. I should say an overall moment there, an overall moment of 8.94 Newton meters, and I would recommend saying anti-clockwise, just to make it absolutely clear which direction that turn is in. Now we're going to look at exactly the same thing again now, but we're going to do it with a slightly different method. Okay, and we always have this choice, and we'll see that we get the same result. So again, we've got 0.3 times 50 anti-clockwise. But this time what we're going to do is think about the component of this force, the component that is perpendicular to the line between this point and the point that we're calculating a moment about. So if we think about where the angles are here, this angle here will be 60 degrees, and so this component, this perpendicular component, will be 10 sine 60, and that is going in a clockwise manner, so I will have 10 sine 60 degrees multiplied by the whole of this distance, 0.7. And again, of course, that comes out as 8.94. Newton meters. And if I compare what I've written down in method 2 to what I had there in method 1, it is actually exactly the same thing. So I've got 10 times 0.7 times sine 60. It's just I've thought in a slightly different way about where that sine 60 has come in. But clearly we get the same result. So you've always got that choice. Whichever seems to make most sense in the situation that you're looking at, you can choose that one. But either method can always be done, and it will always give you the same result. So we're now going to talk about the idea of couples. Now this is where we have two equal and opposite forces, which are separated by a distance d, as in that diagram there. Now because they're equal and opposite, there's no resultant force on the body, but there is a moment, a turning moment on the body, which turns out to be equal to pd, and we call that that moment a couple. So one thing to say about couples is that the moment that we get when we do this p times d is the same as what we'd have if I was to calculate the total moment of those two forces, and that could be about any point at all. So I could pick some random point here as my origin, and if I knew that distance and I worked out the total moment, it's always going to be pd. You can try that for yourself if you are not completely convinced by that. Now in this example, we're going to see if we can work out the couple exerted on this rod AB, which has a length, we're told, of 5 meters, by these forces acting equally in opposite directions, but on different points on the rod. Now we know from earlier what we need to know is the distance that separates those. Now if the total distance of the rod is 5 meters, if we subtract the 1.5 meters there and the 1 meter there, that leaves us with 2.5 meters. So the separation of those two forces is 2.5 meters, and therefore the couple exerted on that rod is the force, which is 20 newtons, multiplied by that separation of 2.5 meters, and so that gives us a value of 50 Newton meters. So that concludes video 1.2, moments and couples. The next video, 1.3, will be equilibrium of a rigid body.